Hello, my name is Brian Sipe, and today I will be presenting our work on optimizing transitions between abstract agent-based model demonstrations. I want to thank the SASO Organizing Committee for giving us this opportunity, as well as for allowing us to present remotely after some unforeseen issues prevented us from attending. I hope that this recording will prove to be informative, and of course will be available afterwards through Skype for any questions you may have. Without any further ado, let's go ahead and get started. This is a brief overview of the topics I will be covering in this presentation. We will begin with a brief summary of the problem we are facing. Next, we will be addressing why this problem is worth solving, as well as possible applications for this type of work. There have been a number of related efforts in this area, so I'll mention some of them, as well as attempt to define why our solution is novel, and why it might be a good alternative to some other methods described. We will follow this with a more formal problem definition that is specific to our work, after which we will review our proposed methods for solving this problem and the resultant conclusions from those efforts. Finally, we'll address some possible areas for future work, and then break for some questions. This slide illustrates in the abstract what we are trying to solve. We have two behaviors, behavior 1 on the left and behavior 2 on the right. Our goal is to transition from one behavior to the other. As there are an infinite number of possible transition paths we could follow, how do we determine which one to take? Well, this problem actually has two parts. The first is defining what an optimal path actually is. This is usually based around the specific use case of the user, but in our case, we will define it specifically a little later on. The second part of this question is, once we have defined what parameter we will optimize on, we have to find a path that satisfies that. One approach to this is to view behavior 1 and behavior 2 in terms of a physical location within a coordinate system. In this case, different transitions will take us to different locations within that coordinate system. Again, our goal is, when starting from behavior 1 on the left, to reach behavior 2 on the right. At each time step, represented by a black dot, we will have a branching factor of 3 in this example, where there are 3 possible locations that our transition techniques could take us. We evaluate, choosing the one that is the closest towards our goal behavior, and then begin the process again until we have reached our goal behavior or any kind of termination threshold we might define. In order to do this, we made use of an agent-based model. In our case, we opted for the AMF Plus framework, which will be referenced a little later. This allowed for agent-level parameters, and with these agent-level parameters being simulated through the use of NetLogo, as seen in the image on the right, emergent swarm-level parameters, or SLPs, can result. These SLPs will then correspond to the spatial location of the agents, and we'll be using that to define the behaviors that we're trying to achieve. We can use images to define the shapes of the flocks. These images will have a series of properties that we had previously defined to be SLPs, a term that we're going to address a little bit later. By using images and not having to be quantifiable, we allow for far less restrictive user requirements. There's a large number of possible applications for optimizing these transition behaviors. Games can apply them as part of AI algorithms. There can be enterprise solutions found for organizational problems, such as supply logistics. Amazon is a good example where this is being put into practice today. The possible uses are only limited by the imagination of the user. Because of this, the wide variety of applications, it is important to use a framework that will allow for sufficient abstraction. Our selection of a framework is outlined next. Much of the earlier work is focused on manually decomposing a task or specifying a task functionally or programmatically. That's not abstract enough for our needs. Don Miner completed some work that would allow us to generate function mappings between ALPs and SLPs. And we built off of that in 2016. This allowed for an abstract demonstration to be utilized. Here we see a summary page of those previously mentioned methods, as well as some of the requirements that might be needed. As we can see, many of the earlier works required manual requirements from input for the user. But the last two did not have any such requirements. Don's work in 2010 still required a numeric demonstration method. Karan's contribution allowed for a simulation image to be used, thus taking the technical requirements off the user and placing it on the framework, allowing for a more tactical use case. Specific to the contributions of this work, there's been a number of efforts in behavior transitions. The first paper by Beal looks at what happens when a sudden environmental change takes place and how the swarm will adapt. An example of this would be placing an object in the middle of the world and the swarm must adapt around it, forming some kind of shape. This was limited because it only explored what would happen if a change occurred, rather than attempting to achieve a specific shape. Beal also provided a way to include functional blueprints as inputs. This is different, but a less abstract input methodology than our problem requires. Finally, Peterson and Nagpal in 2017 looked at optimizing a construction task based on the number of total steps taken by an agent. But this work was limited to spatial arrangements. So now we're going to define what the problem of this specific contribution addresses. We are demonstrating the required behaviors as image or images or video. We're defining a video to just be a collection of images. We're extracting the required swarm level parameters from that demonstration, estimating the agent level parameters required to generate those swarm level parameters, and then verifying that the agent level parameters through simulation match the desired swarm level behaviors. This work focused on optimizing a sequence of behaviors. We simplified this sequence to a pair of behaviors because any number of pairs could be combined in sequence and optimized as individual subproblems. We opted to optimize in the SLP space for our specific problem, though this could be applied to a number of different spaces as desired. In our case, we looked at the transition time or time steps required to reach the desired behavior. Other possible optimization criteria could include the amount of work done, the total steps made, the energy expended, or anything more abstract and defined specifically by the user. Here we see the model sampling in the top of this image. This shows how the training data is generated. There's a number of images. Each image is corresponded to a specific set of agent-level parameters. These images are then featureized to generate swarm-level parameters. These pairings of agent-level parameters with swarm-level parameters are combined to form the training data that is fed into the AMF Plus framework. The user, at each time step, will generate a set of images that they would like to reach. These images are then featureized. The image features are put into the AMF Plus framework. The framework will, over several executions, determine the best ALPs to achieve that desired framework. This will be performed a number of times, and then each image will be simulated, featureized, and compared with the target image to determine the optimal option to use. This will then be repeated until convergence. Our proposed methods make use of a number of shared terminology. First, we have D start and D goal. These are the demonstration images, both the start and the goal image. We have SLP start and SLP goal. SLP start is referring to the swarm level parameters that correspond to the starting image. SLP goal refers to the goal image. Similarly, ALP start and ALP goal are the agent level parameters required and suggested, I should say, by the AMF Plus framework to achieve the SLP start and SLP goal. The output will be a sequence of agent-level parameters. The goal is that by following these agent-level parameters at the given time steps, the swarm-level parameter will be achieved by time step t plus k. In order to define a baseline transition, we opted for an immediate transition. This is to say that at time step 1, we applied the agent-level parameters predicted by the AMF framework directly to the agent-level parameters that it started from. We then observed the changes in SLP space. The second technique we opted to try was ALP-based transition. Here we would be hill climbing in the ALP space. The user would input two demonstrations, the start and end goal. From those images, we would compute the start and goal SLP, then use the AMF framework to predict the start and goal ALP. After some initialization, we would enter a loop where we would take alpha steps towards the goal in the ALP space, the vector between ALP start and ALP goal. We would then simulate all of the resultant images, calculate their new SLPs, then find the argument which was the closest to our goal, add that to the path, set that to our current agent level parameter, and then repeat until convergence. Convergence was defined here and will be in the next method as well as an epsilon from the goal or a maximum number of iterations. The iteration count was necessary after it was determined that convergence was not guaranteed for all methods. The third technique we opted to try was hill climbing in the SLP space. We labeled this SLP-based transition. As with the ALP-based transition, the user would input a series of images. These would be then computed for the start and goal SLP. We would then take alpha steps towards the goal in this SLP space, simulate the desired ALPs to achieve that SLP, simulate them to compute the resultant SLPs for the alpha step, then evaluate to find the simulation that was closest to the goal. This would then be added to the path. We would update our SLP that we're currently at to be the next, and then repeat until convergence, using the same convergence criteria as before. The flocking agent-based model is what we used as an example of this technique. In this case, that represents the motion of birds in a flock. These had 3 agent-level parameters that were present: alignment, coherence, and separation. Alignment was moving in the same direction as the neighbors. Coherence was moving towards a central position in a group. And separation was moving away from other agents. We demonstrated 3 different behaviors. Demonstration A, B, and C on the top right. After looking at quite a few possible SLPs that could be used to define these images, such as the total perimeter, the maximum perimeter, the total area, maximum area, it was determined that only a single SLP was required to achieve maximum separation between the different behaviors. This was the total area of the contours. The bottom right image shows how we achieved this. We were also constrained by the AMF Plus framework to only 3 features. Here we can see the results of those transitions. The purple line represents the immediate transition, the blue the ALP-based transition, and the green the SLP-based transition. The black line is the convergence threshold, and the red X is the convergence point if it achieved. You'll notice that for some of the behaviors, such as B to C, the ALP-based transition did not converge. This is also the case in behavior A to B for the immediate transition. This is probably because the SLP-based transition actively moved towards the goal at every step, while the immediate and ALP-based transition don't actively correct behavior trajectory. Consequently, the immediate ALP-based transitions have a tendency to oscillate near the goal. However, it's worth noting that large error margins may favor the immediate and ALP-based transitions, as you can see in some of the behaviors especially for the ALP-based transitions such as B to C and A to C, where we approached the convergence threshold but did not reach it. Here we can see some of the transition times. They're computed as a mean over and standard deviation over 50 executions. The mean is on the left, the standard deviation is within the parentheses inside. The SLP-based transitions had a significantly faster, on average, conversion time. The SLP-based transitions also had a significantly lower variation in transition time. When evaluating for convergence, using a similar method of mean and standard deviation over 50 executions, we found that the immediate and ALP-based transitions did not have a guaranteed convergence. The SLP-based transition did, however, have a guaranteed convergence. This is because, as mentioned before, the immediate and ALP-based transitions oscillate near the goal. We made use of an existing work that generated mappings between ALPs and SLPs. By making use of this work, we were able to optimize the transitions between abstract behavior demonstrations. We found that the SLP-based transition actively moves towards the goal and provides for a more optimal solution, on average, than immediate and ALP-based transitions. This approach is easily extendable to other agent-based models and transition metrics, as well as various transition trajectories. Some work that's currently being done is a quantitative evaluation of the framework, as well as a comparative evaluation would be useful. Here are some of the papers that were referenced in this presentation. I would definitely recommend reading them if you get the chance. And now I will hopefully be awake to take some questions in the event that I'm not, or that I'm unable to answer your question. Please follow up with any of the 3 people listed here, and we will be happy to try and get you an answer to any questions you may have. Thank you, and see you in a minute.